Hi everybody, welcome back to chemistry. In this video, we're going to go over section 3.7, which is all about changes of state. So remember, state is like solid or liquid or gas. So we say that matter undergoes a change of state when it goes from one state to another. So for instance, we're pretty familiar with melting and freezing. We do that a lot when we cook, right? Going from solid to liquid and liquid to solid. Vaporization and condensation. So condensation you might be familiar with is when you're going from, gas to liquid. And then vaporization is when you're going from liquid to gas. And then these two you might not be as familiar with, sublimation and deposition. Sublimation is when you go straight from a solid to a gas. And deposition is when you go the other way, gas to solid. And we'll talk about those a little bit more in the future. Okay. All right, so melting and freezing. So a substance is melting when it changes from solid to liquid at its melting point, and freezing when it changes from liquid to solid at its freezing point. So water has a freezing and melting point, kind of weird to think about that, of 0 degrees Celsius. So in other words, if you're adding heat, you're melting, and that can happen at 0 degrees Celsius, right? You can add heat and then you're going to go from solid to liquid. And then it also freezes at 0 degrees Celsius. So you can go, if you're subtracting heat or removing heat, you can go from liquid to solid, and that's freezing. Okay, we often talk about it 0 degrees Celsius as a freezing point, but it's also a melting point. Okay, so melting and freezing are reversible processes. So you can add heat and go from solid to liquid, and then you can go back again. And we're familiar with that, right? You can melt water you can melt an ice cube and then go back to liquid again. Solid again, freeze it again. All right, heat of fusion. So the heat of fusion is the amount of heat that's released when exactly 1 gram of liquid freezes. And that's at its freezing point. So this will make more sense in a little bit. It's also the amount of heat needed to melt 1 gram of a solid at its melting point. So it's how much heat is released when you're freezing, when you're going from liquid to solid, right? Let's write that down. Liquid to solid, right? Specifically, 1 gram of your liquid is turning into a solid. It's also the heat required or needed when you when you have 1 gram of a solid turning into a liquid, okay, at its melting point. And this might sound weird. Another way of thinking about it is the amount of heat that's released during freezing, so going from liquid to solid, is the same amount that's needed to go from solid to liquid, okay? So the amount that you put in, the amount of heat that you put in when you're melting something is the same thing that the amount as the heat released when you're freezing something. Okay, so a lot of times we put these ideas in terms of water. So, and that's just because water is very abundant. We work with it often in lab and in science in general. So the heat of fusion for water, for example, is given by this equation. So to melt water, you have, and then let me show you. So this little subscript here, that stands for solid. So anytime you see like a S in parentheses like that, that means solid. So you have solid water, okay? Over here, that L stands for liquid. And you'll see this often. It's kind of like a cursive L often. So you'll see that stands for liquid. And you can put those subscripts after any compound that you have or any chemical that you have, just to let people know, hey, it was in the solid form and now it's turning into a liquid. Okay, so that's what this arrow means. So you could think of this as like before the reaction, and then this would be after reaction. And that we'll get into reactions in a little bit here. Not this video, but in a future video. Okay? So just starting to think of that as before and after that arrow. So the stuff on the left is before, that's before you freeze the water, and then after you get that out. Okay, let me clean this up a little bit. Okay, so to melt water, in order to melt water, let's just put before and after. To melt water, you start with a solid water, right? And then you add in that much heat. So either 80 calories per gram or 334 joules per gram, right? And remember, it's per gram because our heat of fusion is defined per every 1 gram of your liquid or your solid, okay? So 334 joules over 1 gram. There's that imaginary 1 right there. Okay, so in our class, we'll probably look at, we'll use this type of thing more. We'll use joules per gram more than calories per gram, but you should be familiar with both just because you will eventually need to use calories per gram as well. And then remember that your heat of fusion can actually be expressed in conversion factors, and that's what these are, right? So this is the calories per gram conversion factor, and then this is the joules per gram. So remember, thinking back to last week, conversion factors can be written either way. So it either takes 334 joules on the top and 1 gram on the bottom, or 1 gram of water on the top and 334 joules on the bottom. Okay, so that's your heat of fusion, okay? And that's expressed in those conversion factors. So just like in when you're converting things, like converting units, you can use your heat of fusion conversion factors to solve problems. And in fact, we're going to do that in just a second. So when you calculate the heat needed to melt or freeze water, or released when you freeze water, the calculation is heat equals mass times heat of fusion. So this is the heat of fusion, right? This is too, but we're going to use the joules version, okay? So heat equals the mass of the substance you have times the heat of fusion. And the heat of fusion, these numbers, these conversion, well, the actual unit conversion will be given to you. You don't need to know that. In fact, chemists don't usually memorize that kind of stuff. Maybe for water if they work with it a lot. But for heats of fusions of all kinds of different materials, we're not going to memorize all that, right? We can look that stuff up. And then before we move on, I just wanted to remind you or let you know that if you see a G, that stands for gas. Okay? So you might also see H2O and then a G here. That just means gas. All right, so let's try this out. You can pause the video and try it out yourself. I actually think I kind of want to do this first one together because it's a little bit of a more challenging concept. So, how many joules are needed to melt 32 grams of ice at 0 degrees Celsius? How many joules are needed? So that's a form of energy, right? Needed to melt solid to liquid. So let's make some notes here. So we got solid to liquid is our goal, and we want to know number of joules. How many joules? And then we have, what do we have? We are given 32 grams of ice. So let's actually practice writing this out. We know what ice is represented as. We just saw it up in the other slide, H2O with an S next to it. Solid water. Ice, right? If this said water, what would you represent it as? Yeah, it'd be H2O with an L. Usually when you just say water, instead of ice or water vapor, they're talking about liquid water. Okay, so we're given 32 grams of H2O. That's a mass, right? And we want to know the number of joules. Okay, so if heat equals mass times the heat of fusion, and remember we're still dealing with water, how are we going to solve this? What do you think? Yeah, we can set up a conversion factor because we know the heat of fusion. It was given to us. Okay, it was given to us up here. Okay, so let's go ahead and start converting this stuff. So start with what you're given. Remember, 32.0 grams of H2O in a solid form. Okay, we'll set up our train tracks. If you prefer the other method, that's totally fine. Okay, what goes in the bottom here? It goes here. Yeah, grams of water is going to need to go there, right? Because we want to cancel out those grams and get to joules. So let's get rid of that. So how many grams? 1 gram of H2O. Okay, in this case, I guess we could say it's in the solid form. 1 gram of H2O. And then what goes in the top? 334 joules. Yeah, 334 joules. Oops, sorry, capital J, capital J. Okay, and that's what we wanted to get to, right? We wanted to figure out how many joules were needed. Okay, so let's go ahead and cross out our grams of water, right? How did I know this number was 1? Yeah, because down here there's that imaginary 1 in that heat of fusion, okay? You could also see it here, right? And here, okay? If this had asked for calories, you could also calculate that, right? Okay, let's keep going. Okay, so we canceled out our grams of water, and we're left with, make that shorter, we're left with joules on the top, which is what we wanted. So now we got to carry out that calculation. So let's see, 32 times 334 is 10,688. 10,688 what? Yeah, joules. Okay, and that's our final answer. If you wanted, that's a really big number. You could convert to kilojoules, but because the question asked for it in joules, I'm just going to represent it in joules. If you were in lab and you were like, God, that's a big number, I don't want to write that all the time, you could convert it to kilojoules if you wanted to. Okay? All right. Oh, and then, oh gosh, we got to make sure we do our sig figs correctly. So we have two sig figs here, or sorry, 3 sig figs here because of that decimal point, right? So how many sig figs should I have over here? Yeah, I should have 3. So how am I going to represent this in 3 sig figs? Yeah, you're going to have to round. So you're going to have to round up to, let's go, 10,700 joules. Still representing a number that's close to this, this number we originally got, but it has 3 sig figs now. Okay, so let's go. And then you can always write me a little note if you want, 3 sig figs. Okay. All right. I'm confident that we got the right answer. Yeah, we did. Great. All right, then there's sublimation and deposition. So remember, sublimation and deposition are they're ones that you might not be familiar with. Sublimation is when a solid changes directly to a gas. Okay, solid changes directly to a gas. And then deposition is when gas changes directly to a solid. We don't really need to know a ton about this, so I'm just going to move on, but you should know what sublimation is and what deposition is, and then, yeah, that's pretty much all we need to know. All right, so evaporation, boiling, and condensation. Okay, so water evaporates when molecules on the surface gain enough energy to form a gas, right? So going from a liquid to a gas. Water condenses when gas molecules lose energy and form a liquid. Okay, so maybe we should write that. So liquid to gas and gas to liquid. Right? You're familiar with condensation. Happens on your glass sometimes. You're familiar probably with evaporation as well. On a really hot day, if you you went into the swimming pool and then you sit out in the sun, that water is going to evaporate from your skin. You're going to dry off really fast, right? Okay, boiling water. So when water's boiling, all the water molecules are gaining enough energy to form a gas. So they're vaporizing. And the bubbles of water vapor are appearing throughout the liquid. You've seen that happen, right? When you're boiling any water, you see those the bubbles kind of forming there, and then you see some steam, and they're even kind of popping at the top. Okay. And this is just reminding you that during boiling, molecules of the liquid are converted to gas throughout the liquid as well as on the surface. Yeah, so I kind of just represented that, but you know, and then this is probably, you've got a pot or something boiling. Okay, heat of vaporization. So heat, just like the heat of fusion, you would be given this conversion factor, okay? It's not something you need to memorize or want to memorize. It's not really, I'm more concerned that you know how to use the number in a calculation than that you memorize it. So the heat of vaporization is the amount of heat that is absorbed to change 1 gram of liquid to gas at the boiling point. Okay? So just like the heat of fusion was about melting, heat of vaporization is going from solid to liquid or liquid back to solid. The heat of vaporization is going from liquid to gas or gas back to liquid. So we're either thinking of how much heat is required to change from liquid to gas, or how much heat is released when we go from gas to liquid. Okay? And again, we have some conversion factors we can use. So let's break this down a little bit. We got our liquid water. Again, we're using the heat of vaporization for water. So that's similar to the heat of fusion for water. We wanted to compare the heat of fusion for water rather than another substance. There's heats of fusion and heats of vaporization for all kinds of substances. Let's go water because it's easier. So for heat of vaporization for water, you start with that liquid water, and you need this amount, or this unit conversion, or equality is a better way of saying that, of calories per gram. And then you need, or you can also represent that in joules per gram, to get to the gaseous form of water. Okay, so remember that's what that G stands for, is gas, and then this stands for liquid. And then again, we'll probably deal with joules more often, so we're going to look at this conversion factor more than that other one. Okay, and then remember, you can think of this to the left of this arrow as being before the reaction. I'll start writing reaction RXN. Okay, and then this would be after the reaction. After the arrow is after the reaction. Okay, all right, so, and then we call the heat of condensation for water is the heat released when 1 gram of steam, gaseous water vapor, that looks like grams water. That's why we write it like this, H2O gas, changes to water. So we go from gas to liquid, and here we're going from liquid to gas. Okay, so again, breaking this down, we got our gas, our water vapor, right, before the reaction, and then after the reaction, we've got our liquid water, and then we're releasing that same amount of heat that would have been required here to go from liquid to gas. Okay, same amount of heat, right? Okay, so again, you got your 2 conversion factors. Hint, I'm sure you're seeing it coming. There's a learning check. Okay, now we're working in kilojoules. So how many kilojoules are released when 50 grams of steam from a volcano condenses at 100 degrees Celsius? Pause the video, try it out. All right, so what are we given in this learning check? Yeah, we know we're given our mass, right? So let's just say mass in grams. What else are we given? We know that it's going from steam, which is a gas. So from gas to what? It's condensing. So it's going from gas to liquid, right? 100 degrees Celsius is just reminding us that that's the boiling point, right? And we want to know the how many kilojoules. How many kilojoules are released when that happens? Okay, so again, you're not going to need to know this conversion factor off the top of your head, okay? You're going to be given it. So let's set up our equation. So let's start. We got 50 grams of what? H2O in the what? Gaseous form, right? I guess I'll set it up this way for now if you prefer that, just so you can see. Okay, so that's my first one. There's an imaginary one under here, if that helps you. Okay, so what goes on the bottom of my fraction? Yeah, grams of water, right? We want to cancel out those grams of water. So we're going to do 1 gram H2O. I'm going to specify that it's in the gaseous state. Okay, and then what goes on the top? Yeah, 2260 joules. Are we done? Do we want to end up in joules? No, we want to end up in kilojoules. So what are we going to have to do? We're going to have another conversion factor. Okay, so one more conversion factor. We can do this. How many joules are in 1 kilojoule? Remember, kilojoules are bigger. So ask how many of the small thing are in one of my big thing. So 1 kilojoule equals how many joules? Yeah, 1,000 joules. What goes on the bottom? Joules or kilojoules? Yeah, joules. 1,000 joules, because we want to cancel those out. What goes on the top? 1 kilojoule. Yeah. Now are we done? Yeah, because whatever's left in the top is what we want to end up with. We want to end up in kilojoules, right? Okay, let's do some canceling and then we'll do the actual math. So, cancel this. Grams of water, go away. Joules, go away. And we're left in kilojoules, which is what we wanted. All right, let's do the calculation. 50 times 2260 equals 113,000. I'm just going to do the divide by 1,000 without showing it. But you're taking what's on the top, multiplying it together, and then dividing by what's on the bottom. So that's 113. Oh, I wanted that in red. 113 kilojoules. Okay, let's do a quick check for sig figs. We got 3 over here. We got 3 over here, so we're done. Great. Let's box it up to show that it's our final answer. I'm confident that we got that right. Yeah, 113 kilojoules released. Oh, that's a good call too, to make sure that you're writing that they were released, right? That's the amount that was released when we went from our gas to our liquid. So let's go up here and fix our other answer because I want to be more specific. Where'd that go? Oh, up here, yeah. Let's say required to, because we were melting in this case, right? So it's going to require adding that much heat, that much energy. All right, let's go back down. Sorry if I'm making you dizzy. Sheesh, lots of stuff here. Okay, last thing real quick is just heating and cooling curves, and we're actually not even going to go over cooling curves that much because they're just the opposite of heating curves. So heating curve. These are kind of weird. You'll get used to them as you take more chemistry classes, but when I first saw this, I was like, what in the heck is that? It's a weird looking graph. Okay, so let's break this down a little bit. So on a heating curve, diagonal lines are changes in temperature for a physical state, and horizontal lines, plateaus, indicate the changes of state happening. So what does that actually mean? Let's zoom in a little bit. So anytime you see these horizontal lines here, maybe I'll represent those in yellow. I'm sorry, diagonal lines, those aren't horizontal, those are diagonal, those are indicating changes in temperature. So in this case, this is a heating curve, right? So we're showing from, on our x-axis, we're getting from, you know, low heat to high heat. We're adding heat as we go right. And then on our y-axis, we're showing the temperature change, okay? So amount of heat added on the x and temperature change added on the y. Sorry, I had trouble kind of describing that. So on the diagonal lines, you can see that so looking at this solid here, we're heating up our solid. We're adding some heat to our solid, and it's getting closer and closer to temperature of 0 degrees Celsius. And at 0 degrees Celsius, it starts melting, right? What is melting? Melting is going from solid to liquid. So that plateau here is when your ice is turning from solid to liquid, okay? And there's actually no change in temperature there. It's kind of weird. You're still adding heat, but the temperature is not actually changing. And that's just because those molecules are all still changing in, state, okay? Kind of weird. Stick with me. Okay, now looking at your liquid, right? Now we've gone from solid, we've melted, and then we've turned into a liquid. So once you hit that diagonal line here, right there, you're in the liquid state, okay? So in the liquid state, we're going to raise the temperature, right? Throughout that diagonal line, we are increasing the temperature, adding heat, right? And we are still in the liquid phase. When we hit boiling at 100 degrees Celsius, that's when we're going to hit a plateau again. Now you'll notice we're still adding heat, right? We're still going this way on the graph. But our temperature is not actually changing. We're still at 100 degrees Celsius. So that's when you're boiling. That's that whole time on that horizontal plateau, you're boiling, right? What is boiling? Boiling is turning from a liquid to a gas. Okay? So, and then you're going to hit, right, when you stop being horizontal, you've successfully turned into a gas. You've added enough heat where all of your molecules are now in the gaseous state. Okay, so kind of weird, I know. You can also go the opposite way, which is going to be a cooling curve, right? And it's the same kind of idea. What I do want to point out is that I want to just kind of give you this in your notes. So when you're melting, you're going from solid to liquid. That's what this horizontal line is, okay? And when you're boiling, you're going from liquid to gas. And that's what this horizontal line represents, okay? So we'll go blue for horizontal lines. That's when you're actually changing state, okay? In the diagonal lines, you haven't added enough heat to change state yet. I mean, you're still adding heat when you're there. All right, I hope that makes sense. That's the end of this video, and I'll see you in the next one, which will be about chapter 4.